I'm Darcee Caron. I've been learning data analytics with Python for about 2 months, and I'm going to share my first ever Python project with you today. So let's get into it. This project was created as part of a data camp competition, and I used Jupyter Notebook for the coding and presentation of my work. A dataset containing nutritional information about approximately 8,000 different foods was provided, along with some questions to explore. I used Python to explore and clean the data and to analyze the data to respond to the research questions. The project involves using Python to sort and visualize data, compute summary statistics, fit linear and multivariate regressions, and more. This project is special to me because when I undertook it, I had been learning Python for a couple months in a controlled environment. I would watch a lecture, then practice coding with direction and correction in data camp. This project gave me the opportunity for the first time to try coding in Python entirely on my own with no direction. As someone who had literally never tried coding before, I was a bit intimidated and unsure whether and how much progress I was making. And this project made it clear that I had learned so much, and I'm really proud of what I accomplished. I did a lot of analysis and cleaning for this project, so I've decided to use this video to briefly shine a spotlight on some of my favorite bits. First, regarding data cleaning. There are a number of steps I took to clean the data, but the most important and most challenging was to convert the various columns into the correct data type. As you can see here, when checking that all data in a given column was of the same type, I noticed that all nutritional values were in grams, milligrams, and calories, and they included a G, mg, or kcal in the data entry, so instead of being floats, they were strings. I needed to remove the text and convert all the remaining values into floats, and then concatenate the resulting data back to the remaining columns in the data frame. I used the .replace method to isolate numeric values, and then I converted those values to floats, and I used concat to link the cleaned nutrition information back to the ID, the food name, and the food category columns. This was a great learning opportunity because I didn't realize the issue immediately. It was when I began to attempt some calculations that I realized there was a problem with the data, and on investigation, I discovered and solved this problem. Another really interesting learning opportunity came when I was working to identify outliers. I presumed that I would find and subsequently eliminate them. I did find 160 foods with values for calories, cholesterol, and or vitamin C that were outliers. The interesting thing was that I realized that these data represented legitimate and meaningful observations in that I could reasonably assume that the numbers were accurate given the source and because certain foods do in fact contain, for example, much more cholesterol than others. Given this, I did not eliminate any of the outliers. I love investigating correlation, and in fact, this is probably the biggest draw for me to data analytics. It is so cool to use massive amounts of data to find hidden connections between things, or, for example, to discover a lack of connection where we thought there was one. Here, I plotted the correlation between water content and calories. Clearly, higher water content in foods is associated to lower calories. But then I sorted for foods with the highest calorie count, and I noted that they tended to be fats and oils. Water and oil don't mix, right? I wondered what would happen if I eliminated fats and oils from the visualization. In this next visualization, I eliminated fats and oils, and the trend remained the same. Moving on, I examined low-carb foods. I did a subset of zero-carb foods and examined the summary statistics. I've followed a super low-carb diet myself a few times, and so I noted that the mean value for fiber looked low. Following the trail, I plotted out the fiber content, and I discovered that about 7% of the zero-carb foods had a null value for fiber. I eliminated the foods with a null value for fiber, but it made no noticeable impact on the overall nutritional means of zero-carb foods. I started feeling like Sherlock Holmes, and I'm just living for it. I need the hat. So probably my very favorite part of the project is down here, where I plotted correlation of calories to protein, carbs, and fat. I love it because, as mentioned, I love playing with correlation, but also because it was a very tricky bit of code to implement. I found that the coefficients for protein, carbs, and fat are 4, 4, and 9, respectively, meaning that for every increase in a unit or gram of protein or carbohydrate, we expect a 4-unit increase in calories. And for every unit increase in fat, we expect a 9-unit increase in calories. I plotted the correlations here, and then I went on to plot the residuals from calories against each other nutritional information item. All of the residual plots look more or less linear, with the exception in some cases of spread around 0, which could mean that the relationships between the various nutritional categories and calories might be nonlinear. Also, the coefficient for alcohol rounded to the nearest whole number is 7, indicating a positive correlation between alcohol and calories, or in other words, higher alcohol means higher calories. I then did a multivariate regression to examine the relationship between multiple combined nutritional factors and calories. The R-squared value is 0.996, indicating that the model explains about 99.6% of the variance, which suggests the model is a good fit. The F statistic is very large, 2.328 to the power of 5, and the associated probability, the F statistic, is close to 0. This indicates that the overall model is statistically significant. The coefficient for alcohol is 7, indicating a positive correlation between alcohol content of food and calorie content. The fiber coefficient is -2, indicating a negative correlation between fiber and calories. In other words, higher fiber predicts lower calories for a given food item. All the coefficients have very low p-values, indicating that each variable is statistically significant in predicting calories. The large condition number, 4.09 to the power of 3, may indicate strong multicollinearity among the independent variables, or in other words, fat and protein are both correlated to calories, but fat and protein are also likely correlated to each other, for example. Finally, just for fun, I used Seaborn to visualize the calorie content by food category, and I did a sort of color coding gradient. So cool. So if I scroll all the way back up to the top here, you can see my executive summary. So in brief, I found that fruit with the highest vitamin C is the acerola cherry by a huge margin. And other good sources of vitamin C include various pepper varieties, guavas, lychees, and currants. I found that higher water content in foods is associated to lower calories. My analysis demonstrates that the drawbacks of a zero-carb diet is that foods are likely to be higher in calories, fat, cholesterol, and lower in fiber and vitamin C. My analysis also demonstrates that the drawbacks of a high-protein diet is that foods are likely to be higher in calories, cholesterol, and lower in fiber, vitamin C, carbohydrates, and water. My analysis furthermore confirmed that the information provided by the Cleveland Clinic, that a gram of fat has around 9 calories, a gram of protein and a gram of carbs each contain around 4 kilocalories each. And finally, in analyzing the errors of my linear analysis, I discovered that there's a correlation between alcohol and calories. So there is a lot more to explore with this project. If you're interested, I invite you to click on the link in the video description or in my project portfolio, depending on where you're watching this video. Thank you for watching.